In this section, we'll talk about Simulator's ATC tool, Available Transfer Capability. The tool uses linear methods, which are very fast. It uses the same types of sensitivities that are in the PTDF, Power Transfer Distribution Factor, Line Outage Distribution Factor, and Outage Transfer Distribution Factors that are available elsewhere in Simulator. And then it also has some iterated methods that help get more exact answers than can be done just with linear sensitivities. But before it applies those methods, it always makes a guess at the actual transfer capacity using the linear methods because they're really fast. The other thing is that the tool is would be more accurately called an incremental transfer capability because you're always starting with a power flow solution and there's a certain level of transfers that are in the case already, and what it's doing is it's answering how much more power can you transfer between a source and a sink before a limit is reached. It also only looks at thermal limits like transmission lines. It can also consider interface limits, but not voltage limits. PV tool is really what you would use to look at voltage limits. Linear techniques really help when you have lots of different contingencies to look at because it can consider them all kind of simultaneously with the linear technique. If you want to get an exact solution for the transfer capacity for a particular contingency, then you can have it iterate using some power flow solutions, but it can just do that initial screening really quickly with linear methods. So this slide right here just graphically depicts what's going on, and this is if you're using an iterated method that's iterating with a full contingency solution. So as we'll see, that's kind of the most advanced method. But regardless of what method you use, there's going to be linear steps it'll take, and the steps are represented by the arrows that show changes in transfer limits. So if you have a bunch of different contingencies and a bunch of different possible limiting elements like lines or interfaces that could be limiting that contingency, it can consider all of them by first doing a linear estimate of, for example, the most limiting element and most limiting contingency, which would be represented up here, and then it can iterate to find limits that are defined by different transmission lines or different interfaces for that contingency, and then repeat the process for multiple contingencies. Usually you're only concerned with the worst case scenario, so you might want to say just identify the three worst contingencies and the three worst transmission line elements, and so it's not this process isn't going to be infinite. It'll be bound by what you tell it. As I mentioned, you do have to start with a power flow case, a solid power flow case. The list of contingencies is optional, so you can run the ATC just on the base case if you want, or you can run it with a set of defined contingencies. Then you also need to specify a buyer and a seller for the transfer, or a source and a sink. And then the ATC determines how much power can be transferred between those points until a limit is reached, a limit either in a transmission line or in an interface. It's got to look at combinations of limiting element would be like a branch or an interface or a nomogram, and a contingency would be any contingency that's in your defined list, and it's going to look for the maximum transfer for each pair. And if it gives you an answer, say 100 megawatts, that means that you can send 100 more megawatts from the seller to the buyer before you hit the limit defined by the pair of the limiting element and limiting contingency. At this point, it probably makes sense just to bring up a simple example, and then more of this stuff will kind of make sense in that context. So I'll go over to Simulator, and I'll just open, as a simple example, the 7-bus case called the B7 flat. And this case has a already opened line in it, which I think shouldn't be there. All these lines should be in service. So I'm just going to close this one in and then solve the power flow. This will be our starting point. And to open the ATC tool, I go to the add-ons ribbon and then the ATC. And I'll just leave these defaults here. So I'm specifying a seller of area left and a buyer of area right. In this simple case, area left consists just of this generator, area right is just this generator. You can have lots of different object types for seller or buyer. If you're using injection group, of course, you can have a mix of generators or loads in an injection group. A bus is going to be a specific bus in the system that you would identify down here. The slack is going to be the island slack corresponding to the same island that your other part of the transaction is. You wouldn't have them both be slack, but if one end is slack, it's going to be the slack of the island that corresponds to the other part of the transaction. For types, area, zone, and super area, what it means is that all the generators that belong to that area, zone, or super area are going to participate according to their participation factors. So in injection groups, you have participation factors defined with each point in the injection group. So that's how that works. So I'll leave all these defaults as they are just so we can generate some results, and then we can talk about these different options right here. So generally the way you work through this dialog is you start in the options. We'll initially look at the base case only with no contingencies, but we can put those in too. The advanced option, this involves the solution method, which I mentioned. At the core, it's going to use linear techniques to determine transfer limits, but then you can also have it iterate or do full power flow solutions and full contingency solutions to get a more exact answer for your most limiting cases. When I'm ready to start, I go to the analysis page and then just click Start Analysis. And because we're just using linear method, it's really fast. It tells you, when it starts and when it finishes. And then when we go to the results right here, it'll give you pairs of limiting elements and limiting contingencies. Again, in this case, we're not looking at contingencies yet, so every contingency is just listed as the base case. The quantities on that slide will now make sense because we're looking at an example here. What it's saying is that the most limiting element is the line between 2 and 5, the line from 2 to 5, circuit ID 1. On the one-line diagram, it's this line right here. And again, it's saying for a transfer from here to here, this is going to hit its limit first in that transfer, and it's going to do so at a transfer level of about 75 or 79 megawatts. So this generator going up, this one going down for a transfer of 79, then this is going to hit a limit. It also reports sensitivity factors, this OTDF, which is outage transfer distribution factor. There isn't really any outages since we're just looking at the base case, so it's essentially a PTDF between this point and this point. It's saying that for that transaction between here and here, 27% of it shows up on this line, the line that's hitting the limit. So that's the PTDF for that. The pre-transfer estimate, it's not really an estimate in this case because it's based on the power flow solution, but if you're doing an iterated method, it could end up being an estimate of a certain flow before the transfer, especially if you have a contingency involved. And it's not specifically solving for that contingency, it's just going to use LODF to estimate that. It's saying that there's 78 megawatts on this line prior to any transfer, which is what we see right now. the limit that's being used is 100, and that's just the limit for this line. And it's an MVA limit, but it's using it as a proxy for megawatts, even though there's also some VARs on the line. The VAR flow in this case is very small. There's also ways that you can incorporate VAR flows, and certainly if you're doing an iterated method, it's going to actually do a power flow solution at some point. So it's going to take into account the VARs when it does a power flow solution. But in the iterated step, it's just looking at megawatts. The limit is essentially described by what's on this slide. The T sub M is the limit that you see right here, the transfer limit. And with the iterated method, it's just calculated based on those other three quantities. So the limit used minus the megawatt divided by the PTDF. And there's a sign convention which is dependent on how the from and the to bus for the line is defined. So the PTDF could be negative if the line is defined in the direction opposite to where the incremental flow is actually going to go for that transfer. And if that's the case, then you just flip the sign on the limit here, and it's the same thing. Again, that just accounts for the sign convention. If the PTDF is very small, then it doesn't have much of an effect, and the transfer limit is essentially infinite. But you can also tell it to ignore PTDFs that are below a certain threshold too, which normally that's a good idea. If it's an element that isn't really impacted by the transfer, then you wouldn't want it reported in the results. Going back to the example here, the 79.26 is basically just the 100, the limit on the line minus where we started, divided by the PTDF. Gives you that. The next two limits in the list of results are generator reserve limits. This is just saying that area right is going to run out of reserve with a transfer of 200 megawatts. It's basically at that point, this generator is back down to 0. That would limit the transfer. Area left hits a maximum at another 300 megawatts. So that's how much room is left there. But then, because we're just using a linear method, we can just continue to calculate more transfer limits. Assuming these aren't issues, what's the next most limiting issue? And then next up, we have the two lines that are directly connecting the buyer and seller. They're identical lines, and they're both loaded at the same value to begin with, so they have the same transfer limit. They have the same initial value, same limit used, and so forth. And if you're using contingencies, which we haven't looked at yet, then the starting point for the flow on the line is not the current flow, but rather what's called the outage megawatt. So it's going to estimate the post-contingent flow on that line first, and then divide by an outage transfer distribution factor, which is just a combination of the PTDF and the line outage distribution factor. So again, these are the different quantities that get reported in that table. This is what we looked at to set up the calculation. So seller and buyer type, there's several different options for that. The linear calculation method is shown here. The linearized AC is not available. It's shown here and it's grayed out because it's an option when you're doing a PTDF calculation. But the ATC is always going to use one of these lossless DC methods. Of course, you can incorporate the losses and the actual AC system if you use an iterated method. So yeah, and then you can optionally, if you have contingencies defined and you want to ignore them, then you can remove that. In this example, we had all base case limitations, but if you're using contingencies, then you can tell it to ignore anything where the base case is a limiting contingency. generation reserve limitations are what we saw with area left and area right limiters. Then on the lower right side of the dialog, you have these different thresholds where you can say to only show a maximum number of limitations, only show so many per contingency, only show so many per element, and only show up to a certain megawatt value. So those are shown here. There's a maximum of 20 shown, so that means the entire list will not be larger than 20. But then we also have a maximum number per contingency of 10, which is really what ends up being limiting in our case here. We have 10 per contingency. The contingencies are all the base case right here. Let's go ahead and add some contingencies, and we'll see how that affects the results and then also what gets reported. If we go up here to the options and we go to define contingencies, we can just auto insert all the branch outages, for example. And to do that, we'll just right click in the list, the empty list, and we'll go to insert special and then auto insert contingencies. And I'll just leave all these defaults here and choose to insert them. It'll give me 11 contingencies, one for each of the 11 lines in the case. And then I can go back to the analysis page and tell it to start the analysis. And now if I look at my limiters, I'll see that I have some contingencies coming into play. In the first transfer limit that we saw before in the base case is shown right here. It's the 79 on line 2 to 5. In the base case, that's the same result that we saw before. But now these others involve contingencies. So with a loss of one of the circuits between 6 and 7 right here, then you get a lower limit. So that makes sense. If this is out of service, then you're going to get more flow on here just to begin with. And that's reflected in this pre-transfer estimate. So it's using a linear method to say that that's the outage megawatt, basically. It's saying if this line is out of service, then the flow on this line is going to be 87 megawatts, and that's before any transfer between the buyer and the seller. So now the transfer limit is lower because this is higher to begin with. And then the OTDF is different for each contingency because as that topology is changed, then the percentage of the transfer that flows on each element is going to be a little bit different. So that's reflected there as well. Yeah, now we have the max limiters per contingency. We can see that if we sort by contingency, for example, well, looks like we don't have more than 3 or so per contingency, but we have a total of 20 that are reported, so that's more limiting than the number per contingency, and that's shown on the option right here as far as how many total to save, up to 10 per contingency and up to 10 per element. So it doesn't look like either one of those was more limiting than the 20 total, but you wouldn't see more than those amounts specified per element or per contingency. And then the total maximum megawatt limitation here is set to 6,000, which is pretty high. I don't think that ends up being limiting. But if you set that to say 300, then a bunch of these would get lopped off and it wouldn't report those. So we could change that to say 300 and then do the analysis and then look at the list of limiters, and we stop short of 300. So you can also put a threshold in for OTDFs and PTDFs below a certain amount, and it usually makes sense to do that. You don't want to look, especially if you've got a really large case, if you have a distant line that's carrying 1% of a certain transaction, and it's really close to the limit to begin with, then it could end up showing up in your list. But maybe you want to ignore that because the sensitivity is so low. You want to just focus on other elements with higher sensitivities. You can adjust those thresholds. It looks like in this case it's set to 3% for both. The PTDF's applied to the base case and the OTDF's applied to the contingencies. Okay, so this is the example that we've actually already launched that to get some results in there. And there's some other things that you can do on the analysis page too. For the linear method, you don't ever have to abort the calculation because it's so fast, but if we're using some of the iterated methods and it kind of gets hung up, then you can intervene with that button. The increased transfer, again, this is kind of useful for analyzing different states. If you just want to take the case to a certain point, I can go in here to the analysis tab and then say increase the transfer by, say, 100 megawatts. Then it'll go off and actually ramp the 100 megawatts. And I can see at that point I've already exceeded the limit on this 2 to 5 just in the base case. You can explore different transfer levels with that option, and then when you're done and you want to go back to where it was before, you can click Restore Initial State, and then that'll take it back. We kind of talked about these different quantities that are shown right here and how those relate to the calculation of the limit. Those are shown on the slide here too. Yeah, there's also tabs under results, so if you just want to look at branches or just at interfaces or just at nomograms, you can do that too. In this little case, I think we only have limits on our branches and not any on the interfaces, so those are blank. And the branch limiters look pretty much like the all limiters. You can certainly set up ATC analysis to make it go really slow too. I mean, if you're doing iteration and you're trying to get it, calculated to the nearest megawatt, then it's going to take longer. You can also make use of that maximum PTDF, OTDF to ignore limits on lines that are distant or that don't have much of an impact on the transfer. Okay, so next we'll look at these advanced options where we can use these iterated methods if we want. Actually, before we do that, if we're using a single linear step only, I mentioned that it's really kind of by default just using, it's taking the MVA limits and using those as a proxy for megawatts. Really what it's doing is it's ignoring the reactive power, but you can also have it basically derate the limit a little bit by assuming constant voltage magnitude on either end of the line of a limiting element. So the bus voltages being the same as it ramps, and then also just assuming that the reactive power or the megavars don't change. Then as you ramp the real power, then the power factor changes a little bit, and you'd hit a limit a little bit lower than you would if you totally ignored the reactive power. If you're using linear methods and you're also in your limit monitoring settings using amp limits, has to be a provision for using the amp limits instead of MVA limits, and it's going to assume constant voltage magnitude if you check that option. Certainly if we use these iterated methods, then as it gets closer to as it iterates on the transfer limit, it's going to take into account the whole AC power flow. Anyway, this just applies when you use the single linear step, or if you're using these iterated methods, it just applies for the last step that it takes, and we'll see in a moment what that means. Yeah, limit monitoring settings are important. The most limiting value on each end of the line is what's taken into account. Yeah, this just explains some details about those options for, again, the reactive power. if you use this, then the megavars are constant. As the megawatts increase, then the power factor would drop, and it would then be dominated by the megawatts anyway, but it still incorporates a little bit of margin for whatever megavars you have in the reference state or in the initial case. And if you want to incorporate amp limits, then it's going to assume a constant voltage. Okay, so the three different calculation methods, the one that we've looked at so far is the single linear step, and it's the fastest. Then you can also use these iterative methods. So in the iterative methods, it'll actually do a power flow solution after it estimates the transfer level. The difference between the second one and the third one here is that in this one, it's still only solving in the base case. In other words, it won't actually apply contingencies. It'll still estimate the contingent flow with sensitivities. The third one will actually implement the contingency and see how that impacts the actual flows. So, and then they'll iterate. If after the power flow solution it's determined that the limit was exceeded, then it'll take another step where it'll reduce the transfer using linear methods initially to get to a point where it's just on the limit. If the initial estimate falls short and after the power flow solution the limit's still not exceeded, then it can take a forward linear step. So this just explains the loop that goes on. And all these options are on the dialog here where you select the calculation method. So for single linear step, they're all grayed out because it doesn't matter. If we choose the second one, the iterated linear step, then you can have a transfer tolerance. So this basically just tells it when to stop, when it's going to exit that loop right here. It's going to loop through here until it determines that the next linear step is below that threshold, so below 10 megawatts. What we'll see when we go back to the example is that first transfer limit with the contingency was around 30 megawatts. So what it'll do is it'll take a linear step of, I think it was about 34 megawatts, then go out there and actually solve the power flow at that level, and then see if the limiting element, if the limit on the limiting element is exceeded or not. Then it might need to move forward a few megawatts or back a few megawatts. But if it gets to a point where the linear step that it takes is below this level, then it'll stop doing power flow solutions and just estimate the transfer based on that last linear step. Yeah, let's just do that example with those values, and we'll click Start Analysis. And now what it tells me, this highlighting here tells me that it solved this particular transfer with an iteration. So it actually ramped out to whatever the linear estimate was at first. I have to look at what shows up in this log on the analysis to know what the first step was. It says the first linear step was 34.02 megawatts. So that's what it estimated based on the initial linear sensitivities. And it turns out that overshot the limit, because at that level, 34.02, the limit on this element is exceeded for the contingency that applies there. And again, it didn't actually solve the contingency, it's just looking at the linear LODF. But it is solving a power flow, a pre-contingent power flow at this level. And then it sees that it overshot the limit, so then it has to take a step backwards. That kind of goes back to one of those early slides where it had that diagram where it can be jumping forward and backward until it finds the limit. With this next linear step, below the threshold of 10 megawatts, it basically means that at that point it's not going to solve another power flow, and it'll consider it solved. So now, also when it does iterating on at least one transfer limiter, it kind of changes the meaning of this pre-transfer estimate. Remember, what we saw before was that this value was around 80 megawatts or 85 megawatts when we just did the straight linear calculation. Here, the 100.07 is the value after it takes that first linear step of 34 megawatts. It ends up here, and that's why I had to take a step backwards, because this value right here exceeds the limit used. So this was based on the last power flow solution. So you can't directly examine these numbers and then dump them into the equation on that slide that explained what the transfer limit was. You can dump them in from a starting point of that step that it took, that initial step of 34.02 megawatts. All these other values are calculated off of the last solve point, which was right here. So you can tell it on these options here, you can tell it how many transfer limiters to iterate on. So if I set that number higher to say like 3, then it'll find the answer for that first one and then go back and then iterate on these next 2 also. Everything after the last one that it iterates on is calculated based on the last solution that it actually made. If you have a negative transfer limit, what that means is that you have a violation on that element during that contingency even before any transfer is made, and you actually have to run the transfer in reverse in order to relieve that element during that contingency. It will generally report those in the results, but usually you don't really care to iterate on that. That would be a condition that you would assume would have to be fixed before you could do any transfer from the seller to the buyer. So normally you would want to leave this value at 0 or higher than 0, maybe, if you don't want to iterate on very small transfer limits. You know, if I set this value at, say, 50 and then reran it, it's not going to iterate then on those first couple, because those are below, the transfer limit is below that threshold of 50 that I put in, and it iterates on the first 3 that are 50 or greater. Again, normally a value of 0 is normally pretty good to use for that, unless you have some small transfer limits that maybe you want to ignore, or you're going to assume that they're going to get fixed anyway. And then lastly, you can do, the other method you can use is the iterated linear step and then a full contingency solution. Let's just do that, like say on the worst one. So we'll iterate only on 1. And now when I do the analysis, it'll tell me in this log that it's actually solving for that contingency. And it's going to give me a little bit better answer, because instead of applying a linear sensitivity for that contingency, it's actually going to solve the power flow in the post-contingent state. And I get a different color, I get a cyan highlight, which indicates. And there's a slide in the set that explains what all those colors mean. So, I mean, there's different things that can happen. You know, the power flow solution could fail as it's ramping out to the estimated transfer limit, and then it'll give a certain color for that, and other things can happen too. But generally the more common ones are the yellow, which means that it iterated on the transfer but not the contingency, and then the cyan, which means that it iterated on the transfer and the contingency. You can do more of those if you want to, rather than just the first one. You can do like the top 3, and it'll solve contingencies for the top 3 limiters in that case. We get the highlighting there. So yeah, this just explains a little bit more about how it iterates on individual transfer limitations. So each transfer limitation is represented by a line in that results table. So there's a lot of stuff that can go on, especially if you're doing the iterated linear step with the full contingency. And this just explains the different parameters that you can set for iterations and ignoring the stuff that we just talked about. This describes what happens on some of those buttons there. So Power Flow Solution Options just takes you to the Power Flow Solution option, the same stuff that you would get to if you went to it directly. It just allows you to get to it from within the ATC dialog. Injection group options, there's different options on how to do the ramping. If you want megavars to change while you're ramping, checkboxes for allowing only AG-seeable units to vary within the injection group. This is saying as megawatt change the megavar at a power factor of 1. That means that the megavars will stay the same. For the incremental change, it has a power factor of 1. It's all megawatts and 0 megavars, but you can put in a different power factor if you want, or you can tell it to keep the ratio between the real and the reactive power constant at each load, and then scale the megavars by a certain factor if you want to. If you wanted the power factor to stay the same for a load, you could choose that option and then put a 0 in there, and then it would keep the ratio between real and reactive power the same. Okay, so more details on those options shown on the slide here. And if you're doing the full contingency method, you can tell it to iterate on a failed contingency if you want. That's right here. And I think you have to check, you have to check this box here first before you can enable that. Yeah, I mean, that kind of helps you do a sort of PV analysis on a failed contingency, because it'll back off the transfer a little bit and try to get the contingency to solve. If you check this box, it's going to ramp first at the pre-contingent state and then repeat the contingency solution. So that takes a little bit longer than examining the contingencies without that checkbox. But if you're using that, then you can have it also iterate on any contingency that fails to solve. Of course, if a contingency fails to solve as it's ramping, it's really a sort of PV limit that you're running into. So you might want to examine that in greater detail with the PV tool. We mentioned briefly about how the meaning of the transfer limit, so what's shown in that column, is a little bit different if it iterates. We just said if we're doing a single linear step, it's all calculated during the same linear calculation process. But if you're doing the iterated steps, then anything that you don't iterate on is found from the last solution that was iterated on, which we explained earlier. Like, we look at these results here. Everything that gets reported down here is based on a solution at this last point here. Yeah, you get more details as far as the steps it's taking and at what point it does a power flow solution and at what point it does a contingency solution if you're using one of the iterated methods. And again, this shows the color coding that we saw. And as we mentioned earlier, the values that you see at the pre-transfer estimate apply to the last iteration step, or from the last power flow solution. And then these slides explain a little bit more about the different colors that you could see. Some of these are kind of rare. If everything solves properly, then in the iterated methods you'd either see the cyan or the yellow. But if the power flow fails at a certain point, then you might get some of these different color codes. Okay, so another thing that you can do is extra monitor. You can basically define a line or an interface you want to monitor, and then you can provide a sensitivity constant, and this is described mathematically on one of the later slides as far as basically be a criteria to determine whether or not the extra monitor gets monitored. And then you can calculate the flow on that at each stage. If I wanted to define one, we have some interfaces in this case, although they don't have limits on them, so they're not showing up in the results, but we could add those as an extra monitor, for example. We'll go up here to the options, advanced options, and then define extra monitors. And then we could put in, for example, the interfaces. I think you have to do them one at a time, though, I think. insert the 3 interfaces here. I think I have to rerun my results, but then what I could do is I could show the extra monitor values on the results. So if I go to my display column options here, I can see the extra monitor values. I can put those on there. So I can see at each transfer level what's the flow on those. And if you want it, you could use this to help set interface limits, for example. You know, and you could also do it in the PVQV similarly. You could say that at a certain transfer level, you know, I'm going to hit a limit somewhere, and then I just to kind of enforce that limit during that contingency, I can just say that I don't want the flow on this interface to exceed 62 megawatts, because if it does, then I start hitting these limits. And then at higher transfer levels, you know, it keeps going up from there. This one's actually defined in the other direction, so that's why it starts negative and goes the other way. The relative monitor sensitivity constant. If it's larger than 0, then it will ignore, the whole transfer limiter will be ignored if this is not met, if this equation right here is not met. So you can use it to filter out certain things from the result if you put in a relative monitor sensitivity constant. All right, there's also a provision for doing multi-scenario ATC. To do that, you go here to the Advanced Option tab, and you click Analyze Multiple Scenarios. When you do that, there's this whole group of pages that show up for scenarios. And what you can do is you can have different line ratings and zone loads. And this is kind of a proxy for ambient temperature, is what this scenario definition is. Like, the idea is, if you have higher temperatures, if you're looking in the summertime and you have higher temperatures, then your loads might go up, but your line ratings might come down because of the higher ambient temperature. You can have different generator mixes and then different interface ratings. And then so each of these represents a different dimension. So you can have the number of scenarios you have, or basically the number of line rating zone load scenarios, the number of generator output scenarios, and the number of interface rating scenarios all multiplied together. So if you wanted to insert one, for example, with line ratings, we could put in like a few of them here. You would come down here and insert. You'd insert a branch, and then once you insert at least one branch or a zone load, then you can define as many scenarios as you want. So let's just say our branch from 2 to 5 is impacted by different temperatures. And you can do this for as many branches as you want. I'll just use one to keep it simple. Once you create one, then you can specify how many scenarios to use. And maybe we'll have 3 scenarios. And then you can come down here and have to zone loads, for example, and insert. There's just one zone in this case, and it's the whole case. So we'll put that in. 760 is the load in the case right now. And maybe that's the middle scenario. And maybe if the temperature is a little bit lower, then maybe the load is 730 instead of 760. And if the temperature is higher, maybe it's 790 or something like that. Yeah, you can assume that the power factor stays constant as these loads are scaled for these different scenarios, or you can assume that the megavars stay the same. And then maybe with the, again, this is kind of the base case scenario. This is a low temperature scenario. Maybe, the rating goes up to 105, let's say. And if it's a high temperature, maybe it's 95. And then, so this RL0, RL1, and RL2, those are just the names of the scenarios. And you can name them whatever you want. So if you click this button that says Set Scenario Name, you can call this, 15 degrees C. This is 20 degrees C. And then the high temperature, maybe 25 C. So this is just, again, this is just a text field that doesn't mean anything, but it's not going to change anything in the case other than what you have to tell it what the changes are in here, but you can just name them something that means something. And then you can change the B ratings for lines also. I'm not sure what's being used in this case here. I guess if we're in the contingency, let's just set this to use the A rating. So I'm going into my limit monitoring right here, and I'm just going to use the A limits everywhere for normal and contingency. That way I don't have to set up something in here for the B ratings. But anyway, I have a simple scenario defined by temperature with different line ratings and different zone loads. If I wanted different generator mixes, I could insert, at least one generator here, and then I can have more scenarios if I want. So I can have several different generators. I can even have all the generators in my case, and then have different mixes of outputs. And then with interface ratings, I can do something very similar to what I did with line ratings and zone loads. So I can insert an interface here and then have different ratings. But just in the interest of simplicity, I'm going to cut this back down to 1. We'll just have 3 scenarios that are based on these different line ratings and zone loads. So now with these multiple scenarios, when I click Start Analysis and it runs, it's going to do the whole ATC thing for all of my scenarios that I have. When I go to Results, it's going to show me this is the most limiting transfer limiter for each scenario. And I can see, with my lower ambient temperature, where I have a lower zone load and a higher rating, I end up with a higher transfer limit, and vice versa as this goes up. So there's several different ways you can look at the results. If I want to look at all of the results for, say, the 25 degrees C, I can click on that and then say show the transfer limits for that. And then it'll open up another one. And it clarifies up here which scenario I'm looking at. And then it has the results. And then if I want to look at a different one, I can do that. If I want to look at all of them in a single table, I can go down here to Combined Results. So, and then these first 3 columns here will define the scenario by scenario number. It doesn't show like the scenario name there. So there's the 3 scenarios. This stuff doesn't change. So I can see all the different results there. And then if you want, you can also right click on a scenario and say take me to that scenario. And so when I do that, it'll actually change, in this case, the loads and the line ratings. If I look at this line right here, the limit has changed to the limit that I had for that scenario. And the load in the case, so if I go to Case Summary, right here, my load is 790, the amount that's associated with that scenario. And I think when you're done doing all that, if you want to just go back to the initial state, the easiest way is just to restore the initial state. It'll take me right back. These next few slides just explains how you can set up the scenarios with different ratings, different generator outputs. You can quickly develop a whole bunch of them if you use all three of these. And then, yeah, you can dump stuff out to Excel or to text files. If you right click, we looked at take me to that scenario. If you just want to rerun the ATC for a certain scenario, you can also access that option under the determine transfer limit just for that scenario. Returning to the initial state is also pretty handy. More details on each of those options on the slides. And yeah, again, you can also look at one table with all the results in them.
If you need further assistance, please feel free to look us up on the web, give us a call, send email to our support line, or if you prefer to work with a particular Power World engineer, please feel free to contact that person directly.